So we have heard now about a new formula that is available, the Barrett formula that's available on the LENSTAR, and we've heard Adi talk about the results with that formula. And we're very excited to announce that very soon we will have another amazing formula, truly remarkable formula that Warren Hill is going to discuss with us now.
Are we up? Are we up? I don't see it on the screen here.
Yeah, we're not on the screen yet.
There we go. Okay, well, nice to see all of you. And I'm here to share with you something that's very, very exciting, something completely new. And my thanks to Haag-Streit for really their unwavering support over the last 7 years of this project. We're going to talk about a completely new way to do lens power calculations that doesn't use formulas. It uses a form of artificial intelligence and pattern recognition. And I think you're going to be excited by what I'm going to explain to you how this works, and then Mike Snyder is going to show you the results of the very first prospective study. But actually, every person on the dais here has been involved in this project either as a core investigator or as a beta tester. And in fact, a project like this can only happen with the work of a lot of people. We actually currently have 24 physicians participating in 13 countries on this, but and also Peter Maloney, our project leader at MathWorks, one of the largest companies involved in this type of mathematics in the world. These are our core investigators, and not here with us is Lee Wong at Baylor University, who works with Doug Koch, and also David Goldblum, who's a professor of ophthalmology at the University of Basel in Switzerland. And we also have beta testers in Europe, the Middle East, Africa, North and South America, Asia, India, and Australia. In fact, Graham Barrett was very kind to give us cases and work with us early on. So this is a very large project involving the insights and comments and work of many, many people over the last 7 years. So what are we talking about here? We're talking about the elephant in the room. Every time one of us goes into the operating room to implant a multifocal lens, a toric lens, or a monofocal lens where it absolutely positively has to be right, this is always playing in the background for us. And what if we could make this even just a little bit better? That would really be worth something. Now, I've been involved in the Haggis formula optimization for more than a decade, and this is a summary of what we've found over the last 260,000 cases that we've optimized. And although we all think we're really good, it's really less than 1% of surgeons who are in the low 90s for half diopter accuracy. The second tier for this is 6% of surgeons who are about 84%, but the vast majority of surgeons, if you track your outcomes, you're somewhere between 74 and 80%. For this study, 78% comes up a lot, but that's after the removal of obvious outliers and after the optimization of lens constants. So we may not be quite as good as we all think we are. This is what 78% accuracy looks like, and if you're in the multifocal business or the refractive IOL business, I think we need to do better than this for ophthalmology in general. We don't have a lot of time, but I'm just going to explain to you a little bit about how pattern recognition works. And what's the advantage of doing something like this over formulas? Well, pattern recognition has the ability to learn tasks independent of what was previously known. And it also current formulas sort of limit situations to what's already understood. And one advantage of this is it's self-organizing. It creates its own representation of the data. And it's very well suited to the Chinese puzzle, which is the human eye. And think about this. For any given axial length, how many possible combinations are there of ACD, lens thickness, central corneal power, white to white? The numbers go up almost exponentially. So we need something that can handle all these nonlinear relationships. And here's a little example of how a very crude form of pattern recognition works. This is using an artificial neural network. We're going to generate 1,000 random input vectors, put them inside this little box, and ask an artificial neural network to tell us what the internal organization is. And you would think this is almost an impossible task. We're going to use a technique called feature extraction and feature matching, and we're going to run it through a computer 5,000 times and ask us to tell us what the organization is. Now, all of these dots are generated using something called the Manhattan distance generator, and the Manhattan's distance is really just the absolute sum of Cartesian coordinates. It looks like Manhattan city blocks, and that's where it gets its name. So here's 40 cycles, here's 120 cycles, here's 500 cycles, and here's 5,000 cycles, and this seemingly chaotic mess of just random stuff can actually be figured out by this form of mathematics. So the artificial neural network has come up with a self-organizing map. Now we can take this same way of thinking and we can apply it to intraocular lens calculations. There are a number of different tools. They're not exactly household terms: Gaussian process methods, stochastic process methods, Kriging, polynomial models. We ended up with something called radial basis functions just because of the way it interpolates data. So we have a data point here and a data point here and a measurement points in between. We have a very sophisticated way of interpolating the data in 4 dimensions to come up with the right answer. This is very powerful, very exciting stuff. And with the scary fast computers that we now have available to us for large corporations like MathWorks, we can do some pretty stunning work. Now you would think radial basis functions, that's a pretty exotic, kind of geeky mathematical term. It turns out that probably every single one of you that has an iPhone in your pocket is using radial basis functions, and it's all around us. So here near the Gulf of Mexico, where the oil industry has a big presence, when they want to find how an oil field behaves, radial basis functions are used to map that behavior. The agriculture industry, the automotive industry, the motorcycle industry uses radial basis functions almost ubiquitously for the common things like spark plug timings and to calibrate engines. When the law enforcement wants to find the bad guy, they use radial basis functions for pattern recognition to identify facial features. And for the forward forecasting financial people, this is like standard operating stuff for them. So people who are looking to see how the Dow Jones Industrial Average is going to behave or how this stock is going to move through the next quarter, radial basis functions are used for that. Other things like the audiology people use it to get rid of noise. If you have an iPhone and you put your fingerprint on it to identify yourself, chances are the program that identifies you is based in radial basis functions. And because this is pattern recognition, certain branches of medicine really like this, like cardiology. What's a rhythm strip? It's nothing more than a pattern. And this is an example of an arrhythmia that can be overlooked very easily if you have microvolt variations in the amplitude of the T wave after the QRS complex. It can be a marker for sudden cardiac death. So this is used to identify things like torsades de points and T-wave alternans. So how do we develop a calculator? And again, this is a 7-year project that we've been working on a lot, and we use the Haag-Streit LENSTAR because this was really, we had the best measurements, the highest density autokeratometry, axial measurements, all by optical biometry. So we chose this instrument in order to do this. So again, we don't have a lot of time, but I'm going to show you basically how this works, and then I'll show you some of the basic results. We took 13 different variables except for mother's maiden name, shoe size, favorite dessert, and things like that, and came up with what we thought were the most important 13 variables. It's things like pupil size, spherical aberration, white to white, lens thickness. We did some brute force computer modeling and determined that axial length, central corneal power, anterior chamber depth, and a spherical equivalent for a given IOL power were the four most important parameters we needed to look at. We took this organized pattern of data and then ran it through the radial basis function activation functions at MathWorks, and then compared what we got to what we knew was correct from our database called a training set. And then, like finding those little dots in the square, we ran this through again and again until the accuracy increased. And this is done by something called a backward propagation phase, where we feed things back and it mathematically adjusts some things called weights. And it's amazing how accurate you can get this if you have enough data. With some of the initial testing we did, one of the first things that popped out was that there's no calculation bias. This methodology doesn't know that it's a long eye or short eye. All it knows is it's a pattern. And it does the best where it has the greatest amount of data. So this is one of our very first efforts of about 600 and something cases. This is our half diopter accuracy, and these are the cases where that just fell outside the half diopter. So right from the beginning, we knew that we were onto something pretty nice. Now, one of the problems with ophthalmology is it's full of ophthalmologists. And if you want to solve a problem in mathematics and physics, you don't ask ophthalmologists. Who do you ask? You ask physicists and you ask mathematicians. That's why we went to MathWorks. And totally normal day-to-day types of things that mathematicians use, we in ophthalmology have never even heard of. So one of the engineers at MathWorks said, well, gee, how about a boundary model? I said, you know, what's that? And they said, well, it's something that can increase the safety for your patient and also make your users more confident. And I'll share with you basically what a boundary model is. Those of you with an engineering background know about this. This is a plot of central corneal power against axial length. And what we can do mathematically is we can create a boundary model within the confines of which we can identify the accuracy of the calculation. So this is a boundary model for an early effort in this program, and we can identify the cases where we can't resolve the question, but inside the boundary model, we can predict what the accuracy is going to be like. So what we've done is we've created an IOL power calculation method that is self-validating. This is new ways of thinking. So this is the very first pattern recognition IOL calculator, and Doug Koch probably remembers this, you know, from our early stages. We used Microsoft Excel as a kind of our graphic interface, and below I've shown the boundary model. So we're going to calculate for plano. Here are Ks. This is our ACD. This is our axial length. And you notice that all of the green dots are within the boundary model. So we get an IOL power, and we get a statement. And the statement says that for these 4 clouds of data working in 4 dimensions, we are in bounds, and the accuracy can be predicted for this. This is another example where we have 3 of the 4 dots inside our boundary models. Outside the boundary model is this axial length, and it gives us an IOL power, but, you know, heads up, you know, we may not be entirely accurate. So some of the initial testing for this was pretty exciting. This is our first 681 cases, and what we found was we did a really good job. But this may not be a really accurate method of testing this, because 80% of these cases were actually used to make the algorithm. So that's not exactly, you know, valid. But you can see that compared to the others, we were doing a good job. But again, the formula saw these cases in the beginning when it was used to create itself. So this probably isn't accurate. Next is retrospective testing, and this blew our socks off. This is 13 surgeons in 8 countries. 3,212 cases, and these cases had never been seen by the algorithm. And you can see that we're in the low to mid 90s pretty much for everybody. The only flaw in this type of study is that we were sampling the different boundary models where we knew the outcome. So if somebody came out -1, we would sample the boundary model at -1. And so we had a piece of information that could not be known prior to surgery. So this is really nice, but it's a little bit flawed in that we knew the outcome. But what really got our attention is, remember that less than 1% of surgeons are at 92%, and about 6% of surgeons are at 84%. So really the only way to test this in a way that stands up to scientific rigor is prospective testing. And then Mike Snyder is going to actually show us the results of the first large prospective study of this. Now, in an act of enormous generosity, Haag-Streit has agreed to make available this technology to everyone as an online calculator, and it's free. And this is the URL. It went live 2 days ago, and so all of us will have access to this, and you can use this to do your own calculations. This is what the landing page looks like, and if you want to know a little bit more about it, you just click on "What is this?" Up comes a little explanation. And for those of you who are even geekier than I am, who want to know what radial basis functions are, I'll take you to a Wikipedia page and show you the scary math involved behind this. If you enter the calculator, then you'll be brought into something that looks like this, looks just like the LENSTAR. You can enter your information, and if it's an inbounds calculation, what you'll get is an IOL power. If you're out of bounds, if you put in 15 millimeters for the axial length, you're going to get an out of bounds statement, and you can't use this. For daily use, let's say you have some really bizarre combination of Ks, like Ks of 60 and an ACD of 5 or something like that, and it comes up with out of bounds, then just use some other formula. This website's going to be used for data collection. It's very much like Wikipedia. It's an ongoing process where we're all going to have a stake in the game. Right now it's based on about 3,400 cases. Imagine if we had 340,000 cases, how all of us could benefit from that. And We're all going to be part of the development process. This will be updated at 6-month intervals based on data that we receive. So what we're going to be doing is expanding the boundary model. And unlike, older formulas like SRKT and Holiday 1, this is going to be constantly evolving. So every 6 months, the breadth and depth of the calculation accuracy will be expanded as we expand the boundary model. So this is really just the beginning. So in summary, this is a completely new approach for IOL power calculations through the generosity of Haag-Streit and their sponsoring of this research for the last 7 years. Uses pattern recognition, data interpolation, and a validating boundary model. And the increase in accuracy of this over other methods is really based on increased flexibility in the calculation methodology. This has been optimized for the Haag-Streit LENSTAR. You can use other devices, but because of the increased density of keratometry and the unique form of the axial measurements, this is the device that's meant to be used for this. And personally, I see the future of IOL power calculations as being very bright, and every 6 months, I think we're going to be able to up the game. So that elephant in the room, hopefully, will begin to fade away, and we'll all be doing better because of this work. Thank you.
Thanks, Warren.